Hello everyone, and welcome to today's video lecture, which is on the gamma functional equation. So today we're going to talk about what this functional equation is and how to derive it. It's a very important and interesting property of the gamma function. So today's video is going to do the following. We're going to derive the gamma functional equation. And this is the equation that basically shows why the gamma function so perfectly models the behavior of factorials. So namely, we're going to show that gamma of x plus 1 equals x times gamma of x. And we call this a functional equation and it's known as a functional equation because it relates different values of the same function. So you can see from this equation that it's very easy to determine gamma of x if we know gamma of x plus 1. And that's going to be an especially useful property when we want to determine the values of the gamma function for non-integer inputs. And from this functional equation, we're going to also be able to do something that you probably haven't seen before in your calculus classes. We're going to be able to actually extend the domain of the gamma function beyond the region in which it's initially defined, which is the positive real numbers, to also include negative inputs. So this is going to give us the concept of a negative factorial, which is really cool. But I will add the caveat that this concept of the negative factorial actually excludes negative integers. The gamma function is going to be undefined on those values. So to begin with, let's take a step back to recall what the gamma function is and why it was developed. So you'll remember, hopefully from some of my earlier videos, that the gamma function was developed to extend the concept of the factorial to non-integer inputs. Leonhard Euler had this brilliant idea of developing a continuous function that would interpolate the value of the factorial between the discrete values for factorials, which are of course determined on the integers. So if you want more details on this, you can watch my video on the integral form of the gamma function where I show how Euler derived this. But he discovered that n factorial equals the integral from infinity to 0 of the function t to the n times e to the negative t dt. Euler actually came up with a different version of that integral, which was then modified by Legendre into the form that I've written above. And Legendre also found that it was more convenient to work with a function that's equivalent to n minus 1 factorial, so he introduced this notation gamma of n, which is equal to the integral from infinity to 0 of t to the n minus 1 times e to the negative t dt. So this is, of course, just n minus 1 factorial. We haven't done anything except shift things over by 1. So I'll put a box around this. This is the integral form of the gamma function, which we all know and love. So at this point, some of you might be thinking, why are we even doing a video proving the functional relationship of the gamma function? Because if the gamma function just models the behavior of factorials, then isn't it just obvious that gamma of n plus 1, close parenthesis, equals n times gamma of n? Well, sure, when we think about what the gamma function does, gamma of n plus 1 would just equal n plus 1, close parenthesis, minus 1, close parenthesis around the entire thing, factorial, and we just have to confirm that that equals what's on the right-hand side of this equation here, which is n times n minus 1 factorial. Well, looking at the left-hand side of this equation, the plus 1 and minus 1 cancel each other. And on the left-hand side, I have n factorial, and on the right-hand side, I have n factorial. So it seems very obvious that this functional equation holds. And I agree with you if you're thinking that. It definitely holds when n is a positive integer, and it doesn't take a lot of work to prove it. But we want to prove this functional equation in full generality, because the gamma function isn't just defined on the positive integers. The gamma function is defined on all the positive real numbers. So we can't just rely on the behavior of factorials to prove the functional equation in full generality. We need to do a little bit more work by going right back to the definition of the gamma function. So let's consider gamma of x plus 1 in terms of this integral definition. Gamma of x plus 1 will equal the integral from infinity to 0 of the function t to the x plus 1 minus 1 times e to the negative t dt. This is the integral from infinity to 0 of t to the x times e to the negative t dt. We're back to the integral form of the factorial function that Leonhard Euler discovered. Now, to evaluate this integral, we have a special tool at our disposal. We can integrate it by parts. That's often a fruitful approach when you have an integral that has a product in the integrand, as we do here. And what we do is a variable substitution where we treat one term as the function u of t and the other function as the differential dv of t. So here we'll let u equal t to the x, and then differentiating we have du dt equals x times t to the x minus 1. That's just a use of the power rule. Therefore du will equal x times t to the x minus 1 dt. And we'll let dv equal e to the negative t dt. Then integrating both sides, we have that the integral of dv equals the integral of e to the negative t dt. Therefore, v will equal negative e to the negative t dt. So I'll just erase those intermediate steps and bring those findings up a line. And I'll just put this as a refresher that when we do integration by parts, the integral from b to a, let's say those are the endpoints of integration of u dv, equals u of t times v of t, evaluated at those endpoints from b to a, minus the integral from b to a of the integral of v du. So therefore, applying that formula here, gamma of x plus 1 will equal t to the x, that's u, times negative e to the negative t, that's v, evaluated at our endpoints, which are positive infinity and 0, minus the integral from infinity to 0 of, this is v du, negative e to the negative t, times x times t to the x minus 1 dt. So because one of our endpoints is infinity, we need to take the limit here. So this will be the limit as t approaches infinity of, bringing that negative sign in front, negative t to the x over e to the t, minus negative 0 to the x over e to the 0. So that double negative becomes a positive. And here I have minus negative x. I'm pulling that x out in front since it's just a constant, right? T is our variable that's being integrated. So minus x times the integral from infinity to 0 of t to the x minus 1 times e to the negative t dt. And that double negative becomes a positive. Now, when we review this whole expression, something very interesting is going on in that second term, 0 to the x over e to the 0. Because notice, what happens if we let x equal something less than 0? Well, if x is a negative exponent, then this is equivalent to 1 over 0 to the negative x times 1 over e to the 0, which of course is just 1. But that 1 over 0 to the negative x is a negative number. So this is now 1 over 0 to a positive exponent, and 1 over 0 equals infinity. So the entire expression will diverge. Therefore, we're restricted in our choice of x. For this expression to converge, we have to take x to be positive, to be greater than 0. Otherwise, we're going to have that divergence in that term that I just illustrated. However, if we take x to be greater than 0, we don't have that problem. We get 0 to the x, where x is a positive exponent, all over e to the 0. That just equals 0 over 1, which equals 0. There's no divergence. And in fact, when we take x to be a positive number, that term drops out of this expression. So we've gotten rid of that term. Now let's evaluate what happens at the limit as t approaches infinity in the first term. So we take the limit as t goes to infinity of the expression negative t to the x over e to the t. So I'll move that to the top here. So this is going to be an infinity over infinity type of limit, right? As we let t grow without bound, t to the x over e to the t, both of those terms are going to infinity, so we can use L'Hopital's rule to evaluate this limit. And we already know that if we want this integral to converge, then we need to let x be something greater than 0. But even so, doing that, there are still two cases we need to consider as we apply L'Hopital's rule. So I'll draw 2 arrows to distinguish those cases. In the first case, we'll consider x to be a positive integer. And in the latter case, we'll consider x to be a positive non-integer. So in this latter case, x could be a positive non-integer fraction like 2/3 or 9/7, or a positive irrational number like the square root of 3 or 2 pi. X will still be a positive number, but not an integer. So now let's apply L'Hopital's rule to the first scenario where x is a positive integer. And L'Hopital's rule tells us that if we successively differentiate this limit in this numerator and the denominator, that eventually we discover the limit if it exists. So taking the limit as t approaches infinity, and now differentiating one time, negative x times t to the x minus 1 over e to the t. Remember that e to the t is unchanged by differentiation. We again get an expression that just equals infinity over infinity in that limit as t goes to infinity. So we have to differentiate again, and when we do that, we get negative x times x minus 1 times t to the x minus 2 over e to the t. And again, we need to keep going. But if we do this enough times, actually, if we differentiate this expression x times, then eventually we end up with the expression limit as t approaches infinity, negative x times x minus 1 times x minus 2 all the way down to 1. So in other words, negative x factorial times t to the 0, because we've differentiated x times, all over e to the t. And this limit doesn't just equal infinity over infinity. In fact, the negative x factorial is a fixed constant. T to the 0 is always going to just equal 1. And as t is approaching infinity, looking at the denominator, e to the t is going to equal infinity. So we have a fixed finite constant, negative x factorial, times 1, all over something going to infinity, so the entire expression just goes to 0. So now let's consider the other case where x is a positive non-integer. And here we'll let m be the smallest integer greater than x. So for example, if x equals pi, 3.1415, etc., then m would be 4. So again, we apply L'Hopital's rule, differentiating the numerator and the denominator of the expression negative t to the x over e to the t. We would have the limit as t approaches infinity of negative x times t to the x minus 1 over e to the t. And if x is a positive number that's less than 1, then we're basically done because we already have a negative exponent. T to the x minus 1 would be something negative, so that would go into the denominator, and the entire denominator would be approaching infinity, while the numerator is just a fixed constant, negative x, so that limit clearly just goes to 0 again. But if x is a number greater than 1, we already saw in the integer case for x, we have to do multiple rounds of differentiation. So another round of differentiation would yield limit as t approaches infinity, negative x times x minus 1 times t to the x minus 2, all over e to the t. And we would have to differentiate repeatedly. So if we were to differentiate this expression m times, we would get that it equals the limit as t approaches infinity of negative x times x minus 1 times x minus 2, and so on, all the way down to x minus m plus 1. And if you were expecting me to say there x minus m, take a second to confirm for yourself that it's x minus m plus 1. For example, if m were to equal 4, and we did 4 rounds of differentiation, we would have x times x minus 1 times x minus 2 times x minus 3. So that last coefficient really is x minus m plus 1. Now we've done m differentiation, so these terms are all multiplying t to the x minus m, and this expression is all going to be over e to the t. So I'll bring that up to the top line here, and now we're ready to evaluate this limit, having done m rounds of differentiation in the numerator and the denominator. This equals the limit as t approaches infinity of negative x times x minus 1 times x minus 2, all the way down to times x minus m plus 1, all over t to the m minus x, right? Because we made m the first integer greater than x, when we take t to the x minus m, that's a negative exponent, so we negate it and put it in the denominator. So this is all over t to the m minus x times e to the negative t. Well, that expression in the denominator clearly is going to infinity as t is going to infinity, while the numerator, again, is just a fixed constant. So this entire expression again goes to 0. So the end result here is that no matter what positive number we let x equal, in either case, whether x is an integer or not, the limit as t approaches infinity of the expression negative t to the x over e to the t equals 0, applying L'Hopital's rule in both cases. Again, these are all the cases where x is a positive number, a fixed constant greater than 0. So that was a lot of work, but it pays off because it shows that we can actually cancel that first term in this expression, which is equal to gamma of x plus 1. So now all we're left with is the integral piece of it, and we have gamma of x plus 1 equals x times the integral from infinity to 0 of t to the x minus 1 times e to the negative t dt. Again, stipulating that x is greater than 0. We saw that in cases where x is negative, those terms which we were able to cancel actually diverge. But now, if we look at what we have in that integral there, the integral from infinity to 0 of t to the x minus 1 times e to the negative t dt, that's just gamma of x. So we've actually proved in full generality the gamma functional equation, that gamma of x plus 1 equals x times gamma of x. Again, for all x greater than 0. So let's put a box around this functional equation, which we've worked so hard to prove. And now we're going to actually apply it and show why it's so useful. So for example, if we would like to compute gamma of 3/2, well, we could try to compute it by brute force just using the integral definition of the gamma function, but we already know that gamma of 1/2 equals the square root of pi. And if that's unfamiliar to you, that fact, see my earlier video. So assuming that we know this, that gamma of 1/2 equals the square root of pi, then this is very easy to compute, because gamma of 3/2 just equals gamma of 1/2 plus 1. And by the gamma functional equation, this must equal 1/2 times gamma of 1/2. And that, of course, would just equal 1/2 times the square root of pi. How cool is that? Now, the whole beauty of a functional equation is that if we know the value of the function in one place, we can determine the value of the function somewhere else. So we would love to extend this functional equation to include negative inputs. I mean, it seems on the face of it, for example, that we should be able to solve for gamma of negative 1/2. Just plug in negative 1/2 into the gamma functional equation and see what you would get. But if you've been paying close attention to this video, you would say, hold on a second. Because on the basis of the derivation for the gamma functional equation that I've provided so far, we can't do that. Because the derivation of the gamma functional equation was only valid under the assumption that x is greater than 0. It's right there in our boxed formula. The gamma functional equation is only valid when x is greater than 0. Or is it really? I'm now going to demonstrate a technique that's going to extend the domain of the gamma function to negative numbers. And this should really blow your mind if you've never seen it before. And I think this is the first time that it really shows up in calculus of a real variable. And this technique is actually illustrative of a broader phenomenon which we study in great detail in complex analysis called analytic continuation. And here's how it's going to work. Consider the integral form of gamma of x. This equals the integral from infinity to 0 of t to the x minus 1 times e to the negative t dt. And now recall that we proved the gamma functional equation by performing an integration by parts on the function gamma of x plus 1. Well, now we'll consider gamma of x from the same perspective. We'll ask the natural question, what happens if we integrate this expression by parts? Well, sometimes it honestly just takes trial and error, but it turns out that for this integration by parts, the most fruitful approach is to let u equal e to the negative t. So I'll underline that there. U equals e to the negative t. And then differentiating, we have that du equals negative e to the negative t dt. And now we'll let dv equal the rest of this integrand. dv equals t to the x minus 1 dt. And integrating both sides, we have v equals t to the x over x. So now when we do this integration by parts, we have that gamma of x equals u times v, evaluated at the boundaries at infinity and 0. So this will equal u, e to the negative t, times v, t to the x over x, again evaluated at the boundaries infinity and 0. And this is minus the integral from infinity to 0 of v du. So minus the integral from infinity to 0 of t to the x over x times du, which is negative e to the negative t dt. So now this expression, gamma of x, equals the limit as t approaches infinity of 1 over x, right, that's just a constant that I'm pulling to the outside, times t to the x over e to the t, close parenthesis, minus 1 over x times 0 to the x, here we're letting t equal 0, over e to the 0, close parenthesis. And now I'm just going to change that negative sign to a positive because I had a double negative there. So this is plus the integral from infinity to 0, pulling out that 1 over x again in front of the integral since it's a constant. The integral of t to the x times e to the negative t dt, and I'll move that whole expression to the top line there. Well, we know what to do with that first term. That just goes to 0. All of our work on L'Hopital's rule showed that. But I do want to make the following caveat, that we have that 1 over x as the leading term there. It's a constant, but we can't let x equal 0 because then this term would become 1 over 0, which is infinity, and the entire expression would diverge. So now let's evaluate the second term in the expression, which I'm underlining in blue, 1 over x times 0 to the x over e to the 0. Well, again, 1 over x is just a constant term, and it's not problematic as long as x doesn't equal 0. 0 to the x over e to the 0, well, e to the 0 is just 1, and 0 to the x will just equal 0 as long as x is a positive number. If x were a negative number, then 0 to the x would become 1 over 0 to the x, or 1 over 0, and again, we know that's bad, that equals infinity. That has to be avoided. So provided that x is greater than 0, both of those first two terms cancel, and we're left with gamma of x equals 1 over x times the integral from infinity to 0 of t to the x times e to the negative t dt. Again, this relationship holds true provided that x is greater than 0. And in fact, this integral should already be familiar to us. It's just Euler's factorial function. But the beauty of this expression is that it now shows that gamma of x has a divergence at x equals 0, what's called a pole in complex analysis. So this was a worthwhile enterprise. Doing that integration by parts revealed something new about the gamma function for us. It made explicit the pole at x equals 0. And since this seems to be such a fruitful technique, let's try it again. Let's integrate this expression by parts. And so, again, we'll let u equal e to the negative t. And then du will equal negative e to the negative t dt. We'll let dv equal t to the x dt. And then integrating both sides, we'll have v equals t to the x plus 1 over x plus 1. So gamma of x would equal, doing this integration by parts, and here I'm going to move a little more quickly. I'll put it all in brackets. U times v, so e to the negative t times t to the x plus 1 over x plus 1. Again, evaluate at the boundaries, infinity and 0, minus the integral of v du. So this is going to equal double negative the integral from infinity to 0 of t to the x plus 1 over x plus 1 times e to the negative t dt. I'll turn that double negative into a positive, close the bracket, and we have gamma of x equals 1 over x times, open bracket, now evaluating at infinity, the limit as t approaches infinity of, let's factor out that constant term, 1 over x plus 1 times t to the x plus 1 over e to the t minus 1 over x plus 1, setting t equal to 0 here, times 0 to the x plus 1, we're setting t equal to 0 here, over e to the 0. E to the 0 just equals 1, so I'll cross that out. It just equals 1. Plus, I have to make some room. Let's see, let me close the bracket, move the plus sign over a little. Plus, I'll factor out that constant term, 1 over x plus 1, times the integral from infinity to 0 of t to the x plus 1 times e to the negative t dt. I'm sorry if that looks a little cramped. I hope it's clear. And now we can evaluate what's in this bracketed expression. T to the x plus 1 over e to the t by L'Hopital's rule, that just goes to 0 as we let t go to infinity. But let's take a look at that second term that I've underlined. That term 1 over x plus 1 times 0 to the x plus 1 over e to the 0. E to the 0 again just equals 1, so really nothing to say about that. But that 0 to the x plus 1 is only going to equal 0 when? When x is greater than what? Greater than negative 1. Again, we need x plus 1 to be a positive exponent so that 0 to the x plus 1 will equal 0 and this term will vanish. So I don't want to belabor this, but I do want to make it explicitly clear. We need x plus 1, that exponent, to be greater than 0 so that that term in the numerator, 0 to the x plus 1, equals 0, and not 1 over 0 to the negative, open parenthesis, x plus 1, close parenthesis, because that just again equals 1 over 0, which diverges and makes the entire expression diverge. Also, while we're at it, we can't even have x equal to negative 1, because then you'd have a 1 over 0 there. And you'd have 0 to the negative 1 plus 1, which is 0 to the 0, which is also very, very bad. So again, that term only vanishes if x is greater than negative 1. So finally, we have gamma of x equals 1 over x times, those first two terms both cancel, times 1 over x plus 1 times the integral from infinity to 0 of t to the x plus 1 times e to the negative t dt, again, all provided that x is greater than negative 1, and also that x is not equal to 0. Well, this is actually a big deal. This new definition of the gamma function that we've derived is valid for all x greater than negative 1 except for 0. This new definition effectively enlarges the domain of the gamma function for all real numbers greater than negative 1, excluding x equals 0. And here's the real point of this entire video. It's crucial to note, and this is really an amazing fact, is that this new definition of the gamma function agrees with our original definition of the gamma function on all of our values for x greater than 0. But now it gives us some new information. It also defines the gamma function between x equals 0 and x equals negative 1. We've essentially taken the gamma function from the domain in which it's originally defined and continued it to a larger domain. So using this formula, we can now compute, for example, gamma of negative 1/2. We couldn't do that before, but we found an expression that's valid for all x greater than negative 1, so let's do it. Gamma of negative 1/2 would have to equal 1 over negative 1/2 times 1 over, parenthesis, negative 1/2 plus 1, close parenthesis, times the integral from infinity to 0 of t to the negative 1/2 plus 1 times e to the negative t. And now it just takes a little bit of ingenuity to realize that that Negative 1/2 plus 1 is just 1/2, which can be rewritten as 3/2 minus 1, and that just makes this integral into gamma of 3/2, which we already computed in this video a little bit earlier, equals 1/2 times the square root of pi. So putting this whole thing together, we have that gamma of negative 1/2 equals 1 over negative 1/2 is negative 2, and then 1 over negative 1/2 plus 1 is positive 2, so negative 2 times positive 2, times 1/2 times the square root of pi. So we'll just cancel those terms, 2 and 1/2, and we get gamma of negative 1/2 equals negative 2 times the square root of pi. Very cool. And really, why should we stop there? We can do another integration by parts on that expression. And here I'll spare you the details because we've done this integration by parts twice already. We would get gamma of x equals 1 over x times 1 over x plus 1 times 1 over x plus 2 times the integral from infinity to 0 of t to the x plus 2 times e to the negative t dt. And crucially, that expression will be valid for all x not greater than 0 or greater than negative 1, but greater than negative 2. And this expression further shows that gamma of x diverges at x equals 0, x equals negative 1, and x equals negative 2. And again, there's nothing to stop us from doing yet another integration by parts. And if we did that, we would find that gamma of x equals 1 over x times 1 over x plus 1 times 1 over x plus 2 times 1 over x plus 3 times the integral from infinity to 0 of t to the x plus 3 times e to the negative t dt, valid for x greater than negative 3, excluding x equals 0, x equals negative 1, x equals negative 2, and x equals negative 3. In fact, we could repeat this process an infinite number of times, and were we to do that, we would have valid definitions for the gamma function on all the positive and negative numbers, excluding x equals 0 and the negative integers, where gamma of x diverges. So to be more precise, here I should have written gamma of x tends towards positive infinity or negative infinity, because this is what our graph of the gamma function actually looks like on the whole real line, and you can see that it has all these vertical asymptotes at 0 and then the negative integers. Well, that's it for today's video. I hope you enjoyed it, and if you did, please like or subscribe to my channel. Thanks for watching.